we are solving side problems, page 101. Try this problem. Let's see.
Yes, so we have an angle bisector right here, and it gives us AB is 5 and CB is 12. So first, what comes to mind when I think of a triangle and an angle bisector is the angle bisector theorem, which basically says that the ratio of AC to CD is equal to the ratio of AB to BD. So we don't know what AC is yet, but we do know that we have a right angle right there, which means that AC is 13 from the Pythagorean triple. And now we can call DB 5K and CD 13K. And we say 5K plus 13K is equal to 12, which means 18K is equal to 12, which means K is equal to 12 over 18, which is 2/3. So we are looking for BD, so 5 times 2/3, which is equal to 10/3.
That's pretty much nice solution and perfectly understandable. Thank you, Andrew. Ooh, there is another proof. Therefore, this chapter relates to the angle bisector. Let me attempt to prove this one. So AC is, let's put this one as AB, let's put AB is X, then AD is Y. Let's put AC X, Y, and Z. So what we are trying to understand, we will try to attempt to prove 1 over Z equal to 1 over X plus 1 over Y. Under the what condition? If these all three are equal, 60, 60, 60. I feel like 60-degree and angle bisector would be useful. How? Making a parallel line from here to here. So I am going to create a parallel line CK. Do you see that? Let's see. To create a CK parallel to the AB. So once I make a parallel line, there will be, because if there is parallel lines and angle bisector, there will be isosceles triangle. In this case, 60, even more than isosceles triangle. It is going to be, Andrew, what do you see here?
An equilateral triangle.
That is nice, right? So that leads us to putting this value Z here and putting this Z here. Then what do you think the value of this part, this squiggly part?
Y minus Z.
Y minus Z. Great. Now, what do you see? Two similar triangles, right?
Yeah.
Then this triangle, the small triangle, will be compared to what? The bigger one, right?
Yeah.
Okay, let's write down. Can you tell me the ratio, please, Andrew?
Yeah. So
Y minus
the ratio of X to Y.
X to, or let's say Z. Let's start with this way, Andrew. Z to the X, Z over
Y minus Z. Oh, Z over X. That would be equal to Y minus Z over Y.
Y minus Z over
Y.
all things Y, right?
Yeah.
Okay, let's see. I think I feel like we will get something. Z over X. Can we break down this?
Yeah.
Over
Z over Y.
then can I move this z over y to this side and left 1 here,
Yeah.
are we done? Almost, right?
Yeah, just divide by z.
Y by z, which means 1 over x over 1 over y is equal to 1 over z, right?
Yes.
Can I say QED?
Yeah.
What is that? What that? Do you remember, Andrew? You QED?
Yeah.
Good.
Quad arum demonstratum.
Yes, required to prove. Perfect. So we got it, and it will be useful, maybe. Nice, Andrew. I know you have another nice trigonometric solution, but for the time, so let's move to the next one. Okay, now this is page 104, chapter 6, angle bisector side problem. Try this.
Yes. So this one, if you notice, it actually gives us more information, a lot of information. It gives us this, which tells us AD not only bisects MAC, but also MAC is isosceles. So MC, that is 5. And we also have BAC is a right triangle, which means that BC is 10. So this is 5. And now we are looking for DC. So we're just bisecting the angle, which means we should use the angle bisector theorem. So that is 5K, that is 6K. We have that 11K is equal to 5, so K is equal to 5 over 11, which means that DC is equal to 6 times K, which is equal to 30 over 11.
6K 30 over 11. Yep, absolutely great. Then done for this problem. Page 104, side problem. Okay, let's go to, it says challenge. Maybe it will be easier to understand, hard to solve. Let's see. Andrew, how do we start this? Or first of all, do you see that, Andrew, these two strange connection, or one strange connection, A, B, if I say this is Andrew A, then if this is AB is A, DC would be what?
2A.
Did you also find strange? How do we make connection with this A and 2A? What do we do? That's the strange connection. So let's see. Let's attempt to think outside of the triangle. So what do we do, Andrew?
Yes, so we think outside of the pentagon.
That is cool. Let's go to extend. Let's extend from here to here, right?
Yeah.
Let's extend this one. Then when we extend, kind of it's interesting, but it doesn't seem on scale. But what do we see? What do we observe here when we go from here?
So we observe that this is an angle bisector, which means that if we call this E, we have that EAC is isosceles.
So this one and this one is equal, and these two are also equal, right?
Yeah.
We have not still found that connection between A and 2A. How do I connect these two? And I am going to attempt to make another parallel line segment to here to here. Can I do that, Andrew?
Yeah.
Okay, then what's gonna happen when I make these two lines are parallel? What is the value of this
because it's also equal to alpha.
Why? Or in terms of the side. For if this is A, if this is 2A, right?
Side length, then it would be A.
Why?
Because 2A and we have CB is equal to BE, which means that by the similarity ratio, this BF.
Okay, now I got my question almost. Why? Because now I see that there is a connection.
Yes, an isosceles
Got this
triangle.
nice little green, what we call maybe isosceles triangle, right? That will be useful. So let's see how. Okay, let's go angle chasing. Andrew, how do we use angles? So Andrew, if I say this is, let's say this is a beta and beta, right? This is what's gonna happen. This guy is going to be what?
2 beta.
And what about this part?
That's going to be,
Beta, right? Why? Because parallel, right?
yeah, which
Beta.
means that angle DFB is 3 times beta.
This part is 3 beta, and alpha is also 3 beta, right?
Yeah,
Then what do we see this? What about the other part? Oh, if this is 3 beta and then this guy is going to be
3
3,
beta,
and this is also
3 beta, which means that if we add up 3 beta to 2 beta, we get 5 beta, which is equal to 90, which means beta is equal to 18, and alpha is equal to 3 times 18, which is
that's
54,
why we are looking for that angle. Alpha is 3 times beta,
which is
3 times 18 degree, which is
54.
54. Hooray, hooray, hooray. We got it. Ooh, that was a nice problem. Thank you for your help, Andrew. Let's go to another interesting one, Andrew. So do you think our audience, our Geotopian, already worked this problem? Do you think they worked, right? They work hard because
Yes.
until this chapter 6, they have been working very challenging problem, including AMC problems, side problems. Now, they worked on this problem, they try, and the angle bisector, in the topics of angle bisector. Andrew, let's remind our audience this angle bisector theorem one more time.
Yes.
So if this is, let's say this is A, this is B, this is M, this is N, it's angle bisector, A over M equal to B over N, right?
Yes.
Or A times N is equal to M times B. So it could be different ways. So how do we use this only giving information to find this one? Should we think again outside of the triangle?
Yes.
How?
Maybe.
To create, should we create, Andrew, same one here, alpha? Let's see what's gonna happen. Sometimes it's good to try some new figure. And then this is going to be A, right?
Yep.
Then, Andrew, let's suppose this is this guy AD is my angle bisector length, right? Angle bisector of what?
If it did bisect this angle EAC, if it did, then we supposedly B over 2A would be equal to D over C. And we can see that that is the case because if we rearrange things, we get exactly the given, which
Wow, that means
very clever.
this AD is angle bisector, right?
Yes.
Then
2 times alpha is equal to beta.
Wow, what a problem. Alpha over beta would be. Yep. Great. Our audience also can see maybe 5 or 6 different ways when they use their barcode. Barcode direct them to the at the website. There is a solution platform. They can see the trigonometric solution as well.
Yes.
That was end of the chapter 6 side problem.